Hi everybody, it's Friday, November 22nd, 2024, and this is a very short video to discuss aspects of hypothesis testing. In particular, we're going to talk about the level of significance and its meaning, and also in more detail, the power of a hypothesis test. So let's just remember what we're talking about in general. The idea is that we aim to make inferences about a population parameter p. It's going to be a proportion or a probability. And the way we do that is we take a sample, it's random, it's representative of the population, we get a p hat, and we make inferences based on that p hat plus the sample size. And we do that by using a normal approximation. And so inferences are based on the normal approximation, but that approximation holds only provided certain assumptions are also true. So the conditions that we need to be true, the observations must be independent. The sample should be random. That hopefully ensures that the sample is representative of the population. And then the sample size cannot be too big. It can't be more than 10% of the population in the case where the population is finite. And also the sample size cannot be too small. It should be large enough that we would expect to see at least 10 successes and at least 10 failures. So for the rest of this talk, we're going to assume that these conditions hold. And so stating that, since the conditions do hold, we can say that the distribution of p hat is approximately normal. It's going to look something like this. It's going to be a normal distribution, most of which will be between 0 and 1. It's going to be centered at the true population proportion, and it will have a spread or a measure of uncertainty, a standard deviation which we can calculate. So what are the two forms of statistical inference that we've been talking about? Well, first of all, we can make a confidence interval. This provides an interval estimate of an unknown population proportion, and the width of the interval contains information about the precision of that estimate. The less wide the interval, the more precise the estimate. So we've talked about confidence intervals in some detail already. The other thing we can do is we can conduct a hypothesis test. And so what these are for is to see whether a sample proportion is consistent with a null hypothesis. And so here I'm writing the null hypothesis as the true proportion p is equal to p0. So that's going to be some value that will be specified. The test statistic here is computed by standardizing p hat to get a z-score, and then we can calculate areas and probabilities using a standard normal z-table. So that's the background. Now let's get into this discussion about things like level of significance and power. So logically speaking, there are two possibilities. Either the null is true or the null is not true. In other words, false. So that's the truth, and the truth, of course, is usually unknown. We have to make a decision, so we collect data, we get a p hat, we calculate a test statistic, and then we decide whether or not we reject or fail to reject the null hypothesis. So if the null is true, but we reject it by mistake, that's called a type 1 error. Or another way of describing it, it's a false positive. But if the null is actually false and we fail to reject it, that's called a type 2 error, or in other words, a false negative. And so each of these errors has a certain probability of occurring. And so when we talk about level of significance and power of a test, we're really talking about the probabilities that either of these two errors arise. So let's look at this scenario. We're going to assume that under the null hypothesis, the true proportion is some value p0, and we're going to talk about testing at the 5% level of significance. We have three possible scenarios, depending on the kind of test we're conducting. We have a lower tail test, an upper tail test, and a two-tail test. And so here, because we specified the level of significance to be 5%, we know what the critical values will be for each of these tests, right? 1.645 or 1.96. as you can see here. Now the point to make here is if the null hypothesis is true, in all three cases, the probability that we will reject the null hypothesis is 5%. In other words, the probability that our test statistic will be in the red zone in all three cases is 5%. So in other words, the probability of a type 1 error or a false positive is equal to the level of significance of the test. And so we control the probability of a type 1 error. Now let's just talk about type 1 and type 2 together. So again, the probability of a type 1 error when you reject the null hypothesis, even though it's actually true, is equal to the level of significance of the test. So that's something we can control. And so we say that the probability of a false positive is equal to alpha. Alpha is the symbol we use to indicate the level of significance of the test. The probability of a type 2 error, or false negative, that's when you fail to reject the null hypothesis even though it is false, that depends on effect size and sample size. And so most of this video is going to be talking about how changes in effect size and changes in sample size, how they impact the probability of a type 2 error, or the other side of that coin, the power of the hypothesis test. So I also should mention that the probability of a false negative is given a symbol beta. So going back to test power, that's the probability of correctly rejecting the null hypothesis. We said that the probability of a type 2 error is beta. That's the probability that the null is false, but you fail to reject it. Test power, that probability of correctly rejecting the null hypothesis is related to beta. And so I just want to show you what that relationship is. Here we're going to use the complement rule. And so what that says is the probability of any event A is equal to 1 minus the probability that A doesn't happen, right? So the probability that A happens is 1 minus the probability that A don't happen. I think that's quite logical. So let's now specify what we mean by A. In this scenario, event A is the event that the null is correctly rejected. If we correctly reject the null, we're good. The probability of correctly rejecting the null is test power. What is the complement of A? Well, that's the event that the null hypothesis is not rejected. That is a false negative. So if the null is actually false and we do not reject it, A complement is the event that we do not reject it. Right, so point being, test power is the probability that the null is correctly rejected. That's equal to 1 minus the probability that we falsely fail to reject it. In other words, 1 minus the probability of a false negative. And as I said on the last slide, the probability of a false negative is given the symbol beta, and so test power is equal to 1 minus beta. Now, I know this slide is a little bit abstract. I'm mentioning it because I want to be sure that if in the lab or on an assignment or on the final exam, the symbol beta comes up, you're going to understand what it means, right? So beta is just the probability of a false negative. 1 minus beta, the complement, is the probability that you correctly reject a null. That is test power. Right, so we will not learn here how to calculate test power. It is possible to do a calculation, but it's not something we do in this course. However, you will be shown in the rest of this video that power increases with effect size, meaning as the effect size gets larger, the probability of correctly rejecting the null moves closer to 1. And power also increases with sample size, meaning as the sample size gets larger, the probability of correctly rejecting the null also moves closer to 1. So what I'm going to do in the next several slides, using diagrams, is show you by demonstration why these two statements are true. Okay, so now let's look at a more concrete example. Here we're going to assume that the proportion under the null hypothesis is 0.20. And so the distribution of p hat under the null will look something like this. Furthermore, let's suppose that the sample size is 400. And so in that case, we can calculate the standard deviation. It's 0.02 or about 2%. Now, why do we need the standard deviation? Because if we were actually conducting a hypothesis test, we would get a p hat, and then we would standardize that p hat to get a z-score. And then, of course, we would then go to a z-distribution to figure out if we're going to reject or not. And so this is the way we would normally do it. If it's a 5% test, we need a boundary point that puts 5% in the upper tail. And so that critical value is 1.645, as we know. That puts 5% in the upper tail. We now have our rejection region. If our test statistic, our z-score, falls in the red, then we will reject the null hypothesis. Now, this is all great. This is the way we would normally conduct a hypothesis test. But to talk about test power, it's easier to talk about it in the context of the distribution of p hat instead of the distribution of standardized p hat. So instead of the normal distribution, we're going to go back and look at the distribution of p hat under the null hypothesis. And so to make the discussion, we first need to figure out where our decision rule is, where that boundary point is going to be, and where the rejection region is. And so as it turns out, to conduct a 5% test, we're going to reject if p hat is bigger than 0.2329. And how do I know that? That's because if I standardize 0.2329, I see that that value is 1.645 standard deviations above the mean. And so the area to the right of that boundary point, 0.2329, it's also 5%. And so here we could conduct a 5% test, and we would say if our p hat is bigger than 0.2329, then we will reject the null hypothesis. Now here's the question. What if the true value isn't 0.20, but it's something else? So if it is 0.20, the only error we can make is a false positive. So if the null is true, then the probability that we make a type 1 error, falsely rejecting the null, is 5%. But if the null is false, then rejecting the null is no longer an error. The problem is, if the null is false, we might fail to reject the null. In that case, we would be making a type 2 error. So if the null is false, we wanted to detect that it actually is false. And the probability of detecting it is the test power. Right. So here what we'll do, let's suppose that the true proportion is 0.22. So now the true distribution of p hat is going to change. It's going to be centered at 0.22. It's also going to be a bit shorter and a bit wider. And why is that? You just recall that the distribution of p hat is widest when the true proportion is 0.5. And so the closer the true proportion gets to 0.5, the wider the distribution is, and therefore the shorter it has to be as well. And so here 0.22 is a little bit closer to 0.5 compared to 0.20. And so the distribution, the true one, assuming the true proportion is 0.22, that distribution is a bit shorter and a bit wider than what we are assuming under the null hypothesis. Now here's the question. In this scenario, what is the probability that we will correctly reject the null hypothesis? In other words, what is the power of the test? Well, we're going to reject the null hypothesis if p hat is to the right of our boundary, which is 0.2329. In other words, we're going to reject the null if p hat is in the red zone. Right? So if the true proportion is 0.22, then the probability that p hat will be in the red zone is equal to the area under the curve from 0.2329 to the right. It's just this area. And so that area represents the power of the test. So if we put in some numbers, we could actually calculate what that area is, but you're not going to need to know how to do that. The only point is to understand that that blue shaded region is the power of the test. It's the probability that we will correctly reject the null hypothesis. Okay, so just to make sure we all understand what's going on. So on the left, we have the distribution of p hat under the null hypothesis. On the right, we have the true distribution of p hat. The distance between the mean values of those two distributions is called the effect size. In this case, the effect size is 0.02. So the question we're going to ask is what happens to the power of the test if the effect size is increased? So let's suppose the true proportion isn't 0.22, but 0.25. What that does is it moves the true distribution a little bit to the right. So we're going to put that one aside and put in the new distribution. Notice it's a little bit shorter and a little bit wider because 0.25 is closer to 0.50 compared to 0.22. So as we move the distribution closer to 0.50 at the center, the distribution becomes shorter and wider. So there's the center of our distribution, and now you see the effect size is much larger. So increasing the effect size, what impact does that have on test power? Well, the power of the test is now greater than it was when p true was only 0.22. And how can you tell? Well, now look at the area to the right. Again, we're assuming the null is true, and so we're going to reject the null if p hat falls in the red zone. And now, given that the true distribution is the one on the right, you can see that the probability under that distribution that p hat is in the red zone is a very big number. It's the blue shaded area. So increasing the effect size increased the power of the test. Now here we're just comparing the two scenarios. In the top, that was when p true was 0.22, the effect size was 0.02, and the blue shaded area is the power of the test. In the second scenario, the true proportion was 0.25, so the effect size was 0.05, and you can see the power of the test, that blue shaded region, is now much larger. So again, the larger the effect size, the greater test power. What impact does that have on the probability of a type 2 error? The greater the test power, the smaller the probability of a type 2 error. Right, so now we have one more thing to talk about, and that is the effect of increasing the sample size on the power of the test. So here you can see in yellow, that's the standard deviation under our initial scenario where the sample size was 400. And here we're going back to the assumption that the true proportion is 0.22. And so the blue shaded area would be the power under this scenario. And I want you to notice that the power in this case is less than 50%. And how do I know that? Well, if we look at the center of the distribution of p hat, the true distribution, the one on the right, you can see that that center line divides the distribution so that 50% of the area is on the right and 50% is on the left. So clearly, the blue shaded region is something less than 50% of that total area on the right. So we know that test power in this case is something less than 50%. And notice also, just to keep this in mind, that the area in the upper tail of the distribution of p hat under the null hypothesis is 5%. And we made it 5%. We specified that white vertical line, that's the boundary for our decision rule that puts 5% in the upper tail of the distribution of p hat under the null. So now we're going to take a larger sample. What impact will that have on these distributions? Increasing the sample size makes both distributions taller and narrower. So let's see what effect that has. So they might look something like this. Narrowing causes the boundary of the rejection region to move to the left. This is the key idea here. So the boundary where it is, that vertical white line that gives us the red zone, that's going to move to the left. And why is that? Because now that the distributions got skinnier, in particular, the distribution under the null got skinnier, you can see the area in its upper tail is no longer 5%. And so if we use the same boundary, it's no longer a 5% test, it's something much less. So we have to move that boundary over to the left so that the area in the upper tail of the distribution of p hat under the null is, again, 5%. But notice that when that boundary moved to the left, now the rejection region has changed. And so now the probability p hat will be in the red zone, given that the true distribution is the one on the right. That probability is now bigger than 50%. And so power increased. Increasing the sample size increased the power of the test. Right, so that's the whole story. Test power is the probability of correctly rejecting the null hypothesis. You will not need to calculate test power, but you will need to understand why the larger the effect size, the greater the power of the test, and increasing your sample size increases the power of the test. So I hope this short video has helped you to understand this important concept in hypothesis testing. If you have any questions, you can leave them in the comments. You can bring them up in class. You can send me an email. I'll be happy to address them. Apart from that, I hope this video was helpful. Thank you for watching, and I'll see you in class.